so far, the only thing I've discussed is if the source term appears at a node, then you put that in the right-hand side vector. Right? But our source terms really come from physical things, right? We have an injection well here, right? And it might be possible that we could define our mesh such that the well lies right on the boundary. But a lot of times that's not practical. We use some meshing algorithm that just does the best it can, and it may be that that well ends up in the middle of an element somewhere, right? So then what do you do? Okay. So the question is, what happens if Qi is not at a node? Right? So let's look at an element. I'm sorry. Let's look at a body, okay, such that there's some source P that's applied arbitrarily in the middle of the body, okay? And we go then later and we discretize this thing. We discretize it, and it turns out that this is not at a node, okay? So it is some distance, say, XO, from the left-hand side. Well, one thing we can do, we can describe any point source as a function. The function, we'll call it f of x, is p delta x minus xo, where this is the Dirac delta function. So the Dirac delta function is the function defined like this. So is everybody familiar with the Dirac delta function? Right. It's sort of it's a distribution type function. But basically, whenever I integrate something times the delta function, I just get back that something. So another way to think of it is that the delta function returns 0 everywhere except where x is equal to xo. Then it returns 1. Okay. So is that I have my point source defined like a function, well, now I can stick it into the little fi, which is where distributed functions are integrated in the weak form, right? So if I say integrate from x1 to xn, f of x in I of x dx, and I plug in my definition for f of x, what do I get back? Okay? So basically what we do is what this says we do is we use the shape functions to distribute the force to the nodes, right? So if we have one that's interior to an element, we use the shape functions to distribute it to the nodes. And so if we looked at an example where you just had a linear interpolation, so 2 nodes, we had some p applied in the middle. Well, we know the shape functions for that, right? So the shape functions here are n1 is 1 minus x over L, right, if this has length L. And n2 is equal to x over L, right? So then F1 is equal to P1 minus X0 over L, and F2 is equal to P X0 over L, right? And so if X0 were at L over 2, right? So I wrote this generically such that this is X0. But if if now I say, okay, X0 is equal to L over 2, so it's directly halfway, then F1 would equal to P over 2, and F2 would equal to P over 2, right? So it sort of makes sense, right? If I have a source P that's directly in the middle of an element, and all I have is linear interpolation, half of it is going to go there, and half of it's going to go there. But you should do this, it should be consistent with your interpolation scheme. So, just apply the formulas as they are, right? Like this. The X naught is well, in this case we're just talking about one element, so it's local, okay? I just want to be careful because you could define your shape functions in a global sense, and in that case, then the X would need to be global, right? Okay. Very, very soon we're going to talk about isoparametric elements, and everything sort of comes out in the wash in because everything's local at that point. In fact, we just have one parent element that we do all of our integration on. But we have to talk about 2D elements first, and then we'll do that. All right.